Sometimes you do an experiment to measure a quantity, and then you plot the graph, intending to use either the gradient or the intercept to calculate that quantity, and you can't plot maximum and minimum gradient lines because your uncertainties are too small. You want to calculate the uncertainty in your gradient or your intercept because then you have an uncertainty in the quantity that you're trying to calculate. So what do you do if you can't draw max and min gradient lines? Let's have an example. So assuming you've dropped a ball from a height of h and it's hit the ground in a time of t, and you're using this experiment to measure acceleration due to gravity, little g. The equation that relates those two, h is a half g t squared, and so you decided to plot h on the y-axis and t squared on the x-axis, thinking that will give you a straight line through the origin, and then you plot the data. So you do the experiment and you plot the data, and you find something that looks a bit like this. A graph which is straight but has quite small uncertainties. So the uncertainties in the x direction are so small that you can't really see them, and some of the y uncertainties are bigger than the size of the point, but most of them aren't, which means we're not going to be able to draw on a maximum and a minimum gradient line. So what do? We can go back to our original equation. If we rearrange this equation for little g, we find g is 2h over t squared. So if we knew a percentage uncertainty on h and a percentage uncertainty on t, we could calculate a percentage uncertainty on g. And if you can't remember how to do that, look at the video on combining errors. Uncertainty, percentage on g is the percentage uncertainty on h plus 2 lots of the percentage uncertainty on t, noting that there's no percentage uncertainty on the number 2. So, what I need from the data is a percentage uncertainty on h and a percentage uncertainty on t. Let's look at the data. Here's the spreadsheet with the data in it. We have the drop height in this column with its resolution, and we have the drop time squared with its uncertainty. And we've, in previous videos, explained how to calculate these things. So what we can do is we can calculate the percentage uncertainty on the drop height and the uncertainty, on the percentage uncertainty and the drop time. Our estimate of the uncertainty in the drop height is just the resolution, because we've only taken one measurement, so we don't have a spread, so we don't have an uncertainty proper. But we can use the resolution of 0.1 centimeters as our uncertainty. So 0.1 over the value times 100 to give us a percent. Right. So we can calculate the percentage uncertainty in the heights. For the percentage uncertainty in the time squareds, that's just the absolute uncertainty in time squared divided by the time squared. We need to times that by 100 to give us the percentage. Now we have a lot of spurious significant figures here, but that's fine, we will deal with that in a minute. So, we have these percentage uncertainties, and you'll note that they're different for every value. So what's the percentage uncertainty I use when I want to use this equation? What we need to do is use something that I think of as perhaps a characteristic uncertainty. For that, I tend to use the average uncertainty. So let's have the average uncertainty in the height and the average uncertainty in the time, and use those to calculate some kind of estimated uncertainty for little g. So we want the average of those quantities, average 0.5, and average is 1.6. So this is both in percent. So I'm going to reveal an extra significant figure here, because I'm allowed 2 significant figures for percentage uncertainty, so that's 0.52% and 1.6%. So the percentage uncertainty on G is the percentage uncertainty on H, 0.52%. Now, I could have used twice the percentage uncertainty on T, but I instead have used the percentage uncertainty on T squared, which is the same thing. So we've got a percentage uncertainty in total of 2.1%, making sure to round to 2 significant figures, and then I can use that to work out the absolute uncertainty in G, so I can present my value of G to be, let's say, 9.5 plus or minus 0.2 meters per second squared, and then use that in the analysis to say whether my experiment is accurate or not.